In this video, I am going to discuss how to draw the Lewis structure of sulphate ion using basic fundamentals of chemistry. In the first step, we have to draw the skeleton of sulphate ion like this. In the next step, we have to determine total number of electrons that are being provided by sulfur and oxygen atoms for the bonding. Both sulfur and oxygen atoms are in the group 6 of the periodic table. So each sulfur and oxygen atom can give 6 electrons to their valence shell. So let us count down the total number of electrons available for bonding here. There are 4 oxygen atoms, each will give 6 electrons, and 1 sulfur atom will give 6 electrons, and this is an anion with 2 negative charges. That means this ion has 2 extra electrons. So we have to add that 2 also. Altogether this will add up to 32. Now we determine the number of electrons here. So then we have to complete the octet of outer atoms. There are 4 oxygen atoms bonded to sulfur. So we are going to complete the octet one by one. Now we use 32 electrons already because in single bond represent 2 electrons. So if we take one oxygen atom, 3 lone pairs, that means 6 electrons. With these 2 electrons altogether 8. So 8 into 4 means 32. So we don't have any electrons remaining from this 32. So there are no lone pairs going on to sulfur atom here. Now next step is to check the octet requirement of whether the sulfur atom has fulfilled the octet rule here. Sulfur has already 4 sigma bonds, that means it has 8 electrons in the valence shell. But sulfur can violate the octet rule and it can keep up to 12 electrons. So that means it can have another 4 electrons additionally. So we can provide that 4 electrons from this one of the lone pair of oxygen atom and another lone pair of oxygen atom. So this will result double bond like this. So 2 lone pairs, 2 lone pairs, and 3 lone pairs for these oxygen atoms with single bonds. Now our structure has completed up to 80%. Still we have to determine the charges of each atom. So I am going to number oxygen atoms 1, 2, 3, 4. This is sulfur oxygen atoms. So in this method, first we have to write the valence shell electrons. Already we know sulfur and oxygen atoms have 6 electrons in their valence shell, and after that we have to count down the number of electrons belong to one atom. So in this method we take only half of the total electrons from this double or single bonds. For example, if we take this oxygen atom with number 1, there are 4 lone pair electrons, and altogether 4 electrons participate in bondings. But we take half of that, that means 2 electrons. So altogether 2, 4, 6. And there is this oxygen number 3 has same configuration, so it's going to 6. When you come to this one and this one, they have 6 lone pair electrons, and we have to take 1 electron from here. When we come to sulfur atom, it has all together 12 electrons in the valence shell, but we take half, that means 6. Then we can simplify 0, minus 1, 0, minus 1. So that now we can understand. Minus charges go to oxygen number 2 and 4. So now our structure is complete. Now this is the structure we obtained. So you can see 2 oxygen atoms have 2 lone pairs, 1, 2, and 2 oxygen atoms have 3 lone pair electrons. Those oxygen atom bears minus charges because they have reached or they have gained 1 electron additionally. Because of that 1 electron, those oxygen atoms have 1 negative charge. In this section, we are going to explain how to calculate the oxidation number of each atom present in this sulphate ion. So these two are same structure, but this has more explanation. This dot represents the electrons provided by oxygen atoms, and this cross mark indicate the electrons provided by sulfur atom. When consider the oxidation numbers, we have to go to the electronegativity of each element. Here oxygen and sulfur, let us consider simple covalent bond. So oxygen is more electronegative than sulfur. So it can attract the electron cloud towards itself like this. So in this case, the electron cloud displaces. So I am going to write like that. It shift more from the sulfur atom. So because of this, oxygen feels extra electron come towards itself. So it gains extra negative charge. Sulfur feels the opposite direction. It feels loses its electron, so it gains positive charge. So this is for one single bond. So if it is two double bond, we have to consider twice, either 2 negative charge or 2 positive charge. So if we consider here, oxygen has gained extra 2 electron, minus 2, minus 2. Here 1 electron, but already oxygen has negative charge, so again minus 2. So sulfur feels it loses electron, so it gains positive charges, 2, 4, 5, 6. So sulfur oxidation number plus 6, oxygen oxidation number minus 2. Now in this section, we are going to analyze the geometry of sulphate ion. So for this we use VACPR model. It implies valence shell electron pair repulsion method. When consider geometry, we can divide that into two parts. the geometry of electron pairs and the geometry of bonding pairs. The electron pair represent both bonding electrons and lone pair electrons. Lone pair electrons do not participate in bonding. So for this example, we have two single bonds and two double bonds. According to this PSEPR model, we consider all them as one repulsion units. Whether it is double bond or single bond, we consider them as one unit. So then we can understand there are four repulsion units around sulfur atom. So then we have to determine what is the best orientation when there are four repulsion units connected to center atom. Now in this configuration, you can see they are in 90 degrees each other. But this is not compatible because repulsion is higher among bonding pair units. So it rearranges so that one unit is in the whiteboard, that means in the plane of the whiteboard, another unit is in the plane of the whiteboard, and next unit goes from into the plane of the whiteboard, and another one, remaining one, come out from the plane of the whiteboard. So this is the best orientation for sulphate ion. So this is the final orientation of the sulphate ion. It is tetrahedral. So I included two double bonds are in the plane of the whiteboard, and other single bond, one is below the plane of the whiteboard and one is above the plane of the whiteboard. So there is no strict rule that it should be on this way. You can draw that in either way. You can interchange or mix. Double bond can come to any place as seen down here. In this video, we are going to study the hybridization of sulfur and oxygen atoms. So I have numbered oxygen atoms 1 to 4, and oxygen atom 1 and 2 has the same configuration. They have only one sigma bond and 3 lone pairs. The oxygen atoms 3 and 4 have 2 lone pairs each, one sigma bond and one 5 bond. So here the electron configuration of oxygen and sulfur both belong to group number 6 in the periodic table. So these are the ground level configuration. When we consider this oxygen atom, the configuration is written according to the ground state, but the oxygen atom number 1 and 2 already have 7 electrons in their valence shell. So if you are going to consider the ground state, we will get some problem because it doesn't show the correct number of electrons. So we have to add that electron also. So that electron goes to P sub energy level. Now when we consider the hybridization, both oxygen number 1 and 2 have 3 lone pairs and 1 sigma bond. So we have to have 4 hybridized orbital. The role of hybridization is we consider hybrid orbital only for lone pairs and sigma bonds. So here we have to have 4 hybridized orbital. So we can see there is a 1 s sub energy level and 3 p sub energy level. And those 4 orbitals come to one level, 1s and 3p. So we can say we can have 4 sp3 hybridized orbitals. So electrons are not going to change like this. So we can see now these coupled electron pairs act as lone pairs here. Only one uncoupled electron that is going to be used to make the sigma bond. Now we can go to the oxygen number 3 and 4. Those oxygen atoms do not have any charge, means they are neutral position. So they have 2 lone pairs and 1 sigma bond and 1 phi bond. So as in the earlier situation, we do not have to add extra electron because those 2 oxygen atoms are neutral. So the difference here is we have phi bond to consider. So in the rule of hybridization, we do not consider phi bonds in hybrid orbitals. So here then we need 3 hybridized orbitals because there are 2 lone pairs and 1 sigma bond, altogether 3 hybridized orbitals. So we can use 1 from S, 2 from P, 2 electrons, and this to come here, only 1 electron. So 1p remain unchanged. So that electron in p orbital is used to make the phi bond, and these coupled 2 pairs exist as lone pairs, and this uncoupled electron is going to make the sigma bond. Now we can go to the sulfur atom. Sulfur has 4 sigma bonds and 2 phi bonds. To make 4 sigma bonds, we have to have 4 hybridized orbitals. As mentioned earlier, hybrid orbitals do not link with phi bonds. So then we have to have 2 unpaired electrons to make those 2 phi bonds. So we can take 2 electrons from this coupled electron, making 2 electrons, and then we remain like this. So we have to have 4 hybridized orbitals. So we can use 1 from S and 3 from P. So these unpaired electrons in D sub-energy level will be used to make the 2 pi bonds, and these 4 hybridized orbitals will be used to make 4 sigma bonds. This is the final result. Oxygen number 1 and 2 have sp3 hybridization. Oxygen number 3 and 4 have sp2 hybridization. Sulfur atom has sp3 hybridization.